All right, guys. No clever book, no intro today. Let's be honest. It is Sunday, the April 26th, 27th, with 2 days left of class. This is our last lecture. You don't want to really be listening to this lecture. I'm kind of want to get through this lecture pretty quickly and get on with my Sunday. So here's my deal with you is I feel obligated to talk to you a little bit about time series econometrics because this is an advanced econometrics class. You should want to know at least kind of the basics ins and outs of time series econometrics. The In some ways, this topic is the going to be the epitome of the better to teach a man to fish than give a man a fish lecture or idiom, which is that I hopefully have taught you a lot about econometrics over the course of the semester, and more so than you remembering any specific test or topic or derivative or proof that I went over in class, I hope what I've done is I've taught you kind of how to think about econometrics. And so I'm gonna kind of leverage that knowledge for time series. I'm gonna go through these topics pretty dang quickly, with the idea being you guys are now fluent in the world of econometrics. And so even though time series is maybe the most different topic that we've studied, whereas regression discontinuity, difference in difference, and panel data all are kind of similar and have similar goals, time series really, that's working with time series data is very, very different. But I have confidence that you kind of can understand the basics of the terminology and kind of the gist of what we're getting at and go from there. And so I'm going to try to go through all of this pretty quickly. So here we are with time series data, chapter 13 of the Bailey book. And I think there's one more. What topics am I hitting today? So first, just time series data is the idea of correlated errors. So it's non-independent data. You're following a single observation over multiple periods of time. So maybe your time series data, maybe your outcome is the weather, the average high temperature in Los Angeles in July, and your explanatory variables are CO2 levels and population and number of cars on the road or something like that. Or maybe you're studying GDP and your explanatory variables are unemployment and inflation. The idea for all of these things is that there is lots of inertia in time series data. So the weather in one year is not totally independent from the weather the year before that. Same as GDP, is that something that happens one year might have kind of trickling effects or ripple effects that carry on. This can really screw up our idea of especially statistical significance. And so correlated errors and items, I should mention items 1 through 4 on this. I'm going to go through particularly quickly because we do actually cover these in 272, just at a slightly different level. And then stationary data and unit roots, the topic 5. Well, to be honest, I'm also going through it quickly, but is kind of an extra term that comes up a lot. Most oftentimes in time series research, or research that uses time series data, the first part of the paper will be dedicated to proving to the reader that the authors have made their data non-stationary. In other words, if you have that they've made their data stationary. If you have non-stationary data, then you have severe bias in your OLS coefficients, and it's kind of a non-starter. You have to be working with stationary data. That is data that reverts to its own mean. Otherwise, you're kind of estimating nothing, and you're very likely to find spurious results, which I'll show you later on too. Okay. So I think you guys know this. Time series data, I already said this, data that's observed over a single unit of time. I'll use the example of weather throughout this. So our outcome variable is maybe the average temperature in Los Angeles in July, year by year. So first observation in our data set is the average temp in LA in 1970, then 1971, then 72, and on. So autocorrelation, in Econ 272, we call it serial correlation. The more official term is autocorrelation. So serial correlation is just errors being correlated generally. Autocorrelation is when they are correlated across time. And so like I said, it causes the standard errors or causes the estimates of variance to be screwed up and typically underestimated. So your standard errors are too small, your t-statistics are too big, your p-values are too small, you're way, way, way too likely to claim that things are statistically significant. And so kind of a goal of time series data is to remove autocorrelation before estimating the model so that you can get consistent standard errors. The classic model for autocorrelation is this second equation down here, which is that you're estimating the top equation, but your errors take the form of the bottom equation. That is, today's error term is a function of true randomness, and so V is going to be your good true randomness, plus some relation to yesterday's error term. And the correlation between yesterday's error term and today, or last period's error term and today, is going to be given by rho. I think the next slide is going to have this. No, maybe not. So in this example, rho is just related to yesterday's error term. It doesn't have to be the case that it is only one period ago that you're relating to. You could have autocorrelation across 2 periods, 3 periods, 4 periods in something like quarterly data, where you're measuring maybe your temperature every, let's say, 4 times a year. It would be really likely, actually, that if you're measuring weather data quarterly, you might think that you have 4th order autocorrelation. That is, that this period's error term is most closely related to the error term from 4 periods ago rather than 1. All of these are kind of dealt with in the same way, but for mathematical convenience, I'll just kind of talk about first level autocorrelation. So epsilon t minus 1 is the lagged error term. If you're thinking about lagged variables, in Stata, they would look something like this. And Stata actually makes it really easy to generate lagged variables. You just use what's called the L operator that I'll show you in a little bit. But so you would have your outcome, and then the lag of your outcome, which is just 1 period before. So in period 2, the lag of y is the value from period 1. Autocorrelation, just being able to detect it by looking at it is sometimes a little more art than science. So what we have here are 3 graphs going from severe positive autocorrelation to no autocorrelation to severe negative autocorrelation. So obviously, as you go from left to right, things look just a little messier, a little more white noisy. But being able to kind of tell when is something, like the difference between the left and the middle graph, it's clear that they're different, but kind of when have you crossed the threshold of autocorrelation is kind of subtle. It's hard to actually eyeball most of the time, and so we have to rely on statistical tests. Here was the slide. I just didn't jump forward enough. But so again, you can have second order, third order autocorrelation, and something like 4th order autocorrelation is very common in quarterly data, or something like 12th order autocorrelation would be very common in monthly data. Most of the time, autocorrelation is positive. I said this in 272 as well. Technically, it can be negative. Negative autocorrelation would be kind of a severe pendulum example, where if something is really high or really good today, then you know it's going to be really low or below average the next period, and back and forth. Negative autocorrelation is pretty rare in most kind of empirical relevant economic data sets, so we don't tend to focus on it. Most of what I'm going to be talking about is going to be about testing for positive autocorrelation. So to detect autocorrelation, one thing to do would just be to plot your residuals. So you run your regression, y equals beta 0 plus beta 1x, and then you graph your residuals over time and look and see if they tend to be clumped together. So in this case, you have, like 20 years straight with kind of negative residuals. Then here you have about 10 years all with positive residuals, and then you have another kind of 25 years with negative residuals again. That seems non-random. If you were just flipping a coin 25 times, you would never expect to get 20 tails in a row, or 10 heads in a row followed by 20 tails in a row. So this kind of indicates that the error period in one year is related to the error in the previous period. And then this graph would be also still shows autocorrelation, just maybe without a trend. The more formal way of detecting autocorrelation is to use what's called an auxiliary regression, and that is you regress your residual from your regression on the lagged residuals. So in the same way that we calculated, or Stata makes it easy to calculate the lag of an outcome variable, we know we can use the predict command in Stata to generate a residual, and you can also generate lagged residuals. And so you can generate those as variables and you can regress them on each other. This regression isn't necessarily telling us anything terribly meaningful other than the statistical significance on rho. If yesterday's residual is a strong predictor for today's residual, that's an indication that rho is non-zero. In other words, that autocorrelation exists in our data. Yeah, so here's just an example of the Stata code you would need to do, which is, so you're regressing the temperature on the year to see if temperature is rising. You then predict the residuals. You use the tsset command to tell Stata that year is the variable that measures time. And then Stata, I'll show you this in a second in Stata, but the L operator. So L in Stata stands for lag, and so you can simply, you don't even have to generate a new variable. You can say well, in this case they did generate a new variable. You wouldn't have to. But the okay. So to generate the lag of a variable, you just have to use the letter L. So if you want, so we generated the residuals, was called resid of the linear model. To make a new variable that is the lag of that model, you just do L dot the residual linear model. And Stata then automatically goes one period back. If you did L dot, so double lag, then it would go 2 periods back. Or I think you could write in L2 and make it work. In 272, we learned about the Durbin-Watson statistic. This is another way for testing for autocorrelation. It only tests for first-order autocorrelation, but it is probably the most common way to do so. The Durbin-Watson test uses the auxiliary regression and then kind of makes a certain calculation where the rule of thumb for the Durbin-Watson test is that if you get a Durbin-Watson statistic near 2, there's no autocorrelation. If you get a Durbin-Watson statistic near 0, it means there is autocorrelation. There's a table in the back of your textbook or online where you can always just go and look up the critical values. Also, when you just run the Durbin-Watson test in Stata, Stata is smart enough to just tell you whether you're rejecting the null hypothesis or not. So for detecting autocorrelation, we have these kind of 3 methods. Eyeballing it, doing an auxiliary regression, or using the Durbin-Watson test, which is a kind of a more formal version of the auxiliary regression. Now, how do you fix autocorrelation? This is what's called generalized least squares or Praise-Winston least squares. We also talked about this in 272, so I'm going to go through it fairly quickly. But the gist of it is kind of an algebraic transformation, which is you have your model here in 13.1, and you have your error term in 13.2. I'll skip a line and say equation 13.5, this is just the equation for yesterday's outcome or last period's outcome. It's just the same as 13.1, but lagged 1 period. So if 13.2 is true, we can substitute in 13.2 into the error term in 13.1, and that's how we get equation 13.4. Then we can rearrange, so what we want to do, I guess I should tell you the goal and then I'll go through the math. What we want to do is we want to get rid of the correlation between today and yesterday. In other words, we want to transform equation 13.4 into something that does not involve the correlated epsilon term. The VT term, or I guess this is new technically, that is fine. New represents the truly random shock, the truly random uncorrelated part of the error term from this period. So it's okay if VT remains. The way that we're going to get rid of this term is we're going to plug in, so if we look at yesterday's equation and multiply yesterday's equation by rho, that gets us 13.6. And now we see that here we have rho epsilon t minus 1. So we're going to go ahead and plug that in into 13.4. And then we're going to do a bunch of math as well. But this is all kind of straightforward algebra. So the algebra, we go from having plugged it in at the top up here to then combining like terms and then rearranging things to the equation we have here, which is that if we look at the difference between today's outcome and yesterday's outcome, discounted by rho, we reterm the intercept as the true intercept times 1 minus rho, and then we look at today's explanatory variable minus last period's explanatory variable discounted by rho, we have eliminated the serial correlated part of the error. And we can think of this term inside this parentheses, and we can think of this y term inside of these blue parentheses that I just made as kind of new transformed variables. We could essentially generate these variables in Stata, and so we'll go ahead and call the y term y tilde, and the x term x tilde, and the intercept term beta 0 tilde. And so this bottom equation, y tilde equals beta 0 tilde plus beta 1 x tilde plus vt, is a regression equation, a population model that we can run. It's a regression equation we can run where, most importantly, beta 1 is unchanged. In other words, the true impact of a 1 unit increase in x on y has remained the same. So even though we've done a lot of algebra to kind of transform the equation, we haven't transformed the fundamental thing we want to estimate, which is what is the impact of x on y. We've transformed x, we've transformed y, we've transformed the intercept in order to remove serial correlation so that we can then estimate this relationship in a way that will give us unbiased beta coefficients and also unbiased standard errors. Here's an example of if rho were equal to 0.5, here's what kind of the transformed data would look like. So that's kind of where we got in 272, which is that if you have autocorrelation in your data, you can detect it, and then you can correct for it using that Praise-Winston GLS model. Two more topics that I want to talk to you about. One is a dynamic model. A dynamic model is when you actually include the outcome from the previous period on the right-hand side of your equation. So yt minus 1 is included directly into the equation. So the reason you might do this is because it's often true. You're kind of directly modeling the inertia in time series data. You're directly saying that we know that today's value of temperature or today's value of kind of political approval rating or something like that, we know that today's value depends on where we started off in the previous period, that these things only move so much from one time to the next, and then they also might be influenced by explanatory variables. But so by directly modeling this, rather than you can allow yourself to kind of directly estimate this gamma value, which is kind of an empirical estimate of how much does today depend on the day before, which sometimes can be an important kind of parameter to know. Gamma can be, so again, if you're kind of a political party, you want to know from your polling data, if we get a poll this month, how much can we expect, even under extreme circumstances, the poll to change a month from now? Kind of what's our bandwidth of kind of where we're at? You might, same thing with temperature, same thing, I guess the other example I've written down here was inflation. So dynamic models are similar in spirit to standard time series models, except the emphasis is kind of on estimating this gamma parameter, because sometimes it's just something that you really want to know. The implication of dynamic models, however, is that beta no longer really represents the impact of a 1 unit increase in x on y. Why is that? Well, if you think about it, if x goes up by 1 in period t, that's going to have a beta 1 impact on yt. However, yt is then going to be in tomorrow's equation, and yt is impacting yt plus 1, so thus the 1 unit increase in x is not going to just impact yt, it's also going to impact yt plus 1 and yt plus 2, and on and on. So the beta 1 coefficient kind of loses, I shouldn't say it loses a little bit of its meaning, but we need to reinterpret it. And the new interpretation of a beta coefficient, of the impact of a 1 unit increase in an explanatory variable, is that it has a beta 1 divided by 1 minus gamma impact on y over the long run. So if gamma is really, really close to 1, so let's say gamma was 0.9, so then your denominator was just 0.1, a 1 unit increase in x is going to have beta 1 divided by 0.1, which is going to be 10 times larger. So it's going to kind of have 10 times the beta impact on y in the long term, where if gamma is really close to 0, then beta 1 is just going to be uh, beta 1, because the denominator is roughly going to be 1. And so that makes sense, that if yesterday, going back to the dynamic model is here, if yesterday really doesn't impact today directly, then beta 1 kind of just has its old normal interpretation. Um, Including, you shouldn't just by default include y in your model just because, like, hey, why not? Probably it matters, because if you do, unlike when I teach irrelevant variables in 272, and I mentioned that if you include a totally irrelevant variable, if we're measuring the impact of temperature based on CO2, and I include a variable for how many likes did the latest did my latest Instagram get, that's not going to bias the other results. It's just going to kind of hang out there. Whereas if you include y, t minus 1, as your variable, and you shouldn't be, it's going to severely bias things. So kind of proceed with caution. So the last thing I'm going to talk about is stationarity. And stationarity it kind of almost comes before in the process. Like, most papers have to deal with stationarity before they even deal with autocorrelation, because if your data is non-stationary, you're kind of screwed. So let me do a quick example. And I do this example in 272, but I don't really tell you why. So this is the example of a random walk. So what I have here is I'm going to generate two variables that I'll call y_air and x_air, and they're completely unrelated to each other. And so I'll generate these variables. We have 500 observations. I'll run a regression of them, and then I'll show you the scatter plot of those variables. So here's the scatter plot of x and y. Again, it looks kind of like they're uncorrelated with each other. And when we look at the regression, we get a t-statistic of 0.05. Our coefficient is virtually 0. These are two, by definition, completely uncorrelated things. Now, I'm going to turn these variables into what's called a random walk. So I'm going to set up, I'm just going to pretend that the year, so let's look at our data set real quick. So, the year is just kind of increasing by 1 each time. And then I'm going to use that L operator. And so I'm going to generate a variable called y and x, where if we look at them, whoops, what went wrong? Y is an ambiguous abbreviation. Interesting. So I had done this a different way before. Okay, so I'll do this using a loop. I thought I had removed the need to use a loop, but maybe not. Is again an ambiguous abbreviation. Oh, because of the variable year? Well, shoot. So let's call this maybe y2 and x2. y2, x2 to make it less ambiguous to Stata what I'm talking about. Let's give that a shot. Okay. So no reason they needed to be called y2 and x2, but here we are. All right, so y2 is the just kind of the sum of these y errors. So the first value of y2 is equal to the y error, but then the second value is essentially 1.1 plus negative 0.097, and then that plus 0.25, you get that. 1.25 is the sum of these three numbers, and it's the same for the x. So again, the x error and the y error originally have nothing to do with each other. They should be completely uncorrelated. But when we go ahead and we look at these two variables, now that we've kind of set them up in this time series framework, oh, I forgot to update this to 2 and 2. I'll do the regression as well, 2 and 2. So these things kind of look correlated to me now. So, it kind of looks like as the red one goes up initially, the blue one's going down a little bit. So they're kind of negatively correlated. Then as the red one's going down, the blue one's going up. So again, that's a negative correlation. And then they both kind of trend up. So it's maybe a little negative and a little positive correlation. But let's look and see what the regression says. The regression says that they have a t-stat, a statistical relationship of 21.2, p-value of 0. They are highly statistically significantly related. This is what's called a spurious regression. And I could rerun this. I'll change the seed, so I'm generating new data. And once again, the scatter plot of the errors looks unrelated. The graph, whoa, these two look super, super related. I'm guessing this is going to be a t-stat in the 50s, 47.74. Look at me eyeballing t-statistics. And then I'll generate new data as well, do it again. And okay, so these look like, yep, they're both just kind of trending down. And so sure enough, once again, statistically related to each other. The reason for this is that these data have a unit root. They are non-stationary data. And what I mean by that is each subsequent value of this data set is the sum of the previous error terms. And if you think about the variance, that means that each subsequent observation in this data set has a higher variance than the data set before, because it's the sum of the error term from the previous period, which has a variance of 1, plus the variance from the next period, and again and again and again. And so as this variance builds, the data become non-stationary. What non-stationary means is that for each observation in your data set, it does not have necessarily the same variance or the same property. Stationary data is data where at any point in the time span, you would kind of, in expectation, find the same relationship, find the same variance, find the same slope. This is one example of non-stationary data, which is data where the variance is building over time because you're kind of summing all of these errors together without reverting to the mean at all. So stationary data is stationary if it has the same distribution for the entire time series. An example of non-stationary data would be data A with maybe a constant trend, something that's always increasing over time or decreasing over time. Or second, this is the example I just showed you in Stata, a random walk. And so either of these are then going to really kind of screw up your estimates, and they're going to cause severely, severely biased beta estimates. Or what are often called spurious regressions, because no underlying real economic relationship exists, yet you end up estimating a highly statistically significant, strong relationship. So unit root is kind of, again, this was what I showed in that example. A unit root, it would be the equivalent of when gamma is equal to 1. So yesterday is fully dependent, or sorry, today's outcome is fully dependent on yesterday's outcome, and then we just move either a little bit up or a little bit down. If gamma is less than 1, that's going to indicate some amount of mean reversion, so that yesterday is correlated, or today is correlated to yesterday, but you kind of always move a little bit back towards the mean, or a little bit back towards 0. So gamma less than 1 is a standard dynamic model. That's going to be okay. You can use OLS. If gamma is greater than 1, that's going to be called exponential data. Your data is going to explode. And if gamma is equal to 1, you have what's called a unit root. Not good. Your data is likely to be a random walk. You're likely to find spurious correlations. And in truth, if gamma is really close to 1, a little bit above, a little bit below, that's still kind of as bad as having a unit root. So another test that tends to occur in time series papers is showing the readers that you don't have a unit root in your data. So unit roots cause downward bias on the coefficients. The standard errors are not t-distributed, and there's a strong possibility of spurious regressions. And then, actually, I already showed you my simulations in Stata, so I know this was kind of a crash course in time series terminology, what I want you to kind of come away from this lecture remembering is autocorrelation is what we called serial correlation in 272. So you know what autocorrelation is. Oh no, sorry, there was one other term. Sorry. You've got 1 minute left, I promise. So 28 slides, I'm on slide 23, yeah. So, okay, so these simulations were pretty similar to what I already showed you in Stata. On the left are examples of non-stationary data. On the right are then examples of data without unit roots. So you can kind of see the difference between the two. The test for a unit root is called the Dickey-Fuller test. So like the Durbin-Watson test, like detecting autocorrelation, economists have come up with ways of detecting this, but kind of before you even run your first regression or kind of get your first set of results, you need to test for a unit root in Stata. And so the Dickey-Fuller test kind of is a way of estimating gamma. And it has critical values just like the Durbin-Watson test. Sorry, I want to skip this to then just get to the last slide, which is the last term I want you to know from time series is what's called vector autoregressions, VAR models. This is the idea of essentially looking at multiple time series sequences at once. So maybe rather than just looking at the weather in Los Angeles year by year, you're looking at the weather in Los Angeles, San Francisco, and New York. So you have 3 different cities, and you're looking at all of them over time. That's called a vector autoregression because rather than sort of a single time series observation, you're estimating a vector of time series. This would maybe be a 3x1 vector, 3 cities, and you're estimating a time series model for all 3 cities at once. You might say to yourself, well, this equation looks a lot like the equation for panel data. And you would be exactly right. This is the exact same equation as for panel data. So what distinguishes a vector autoregression model from panel data? And the answer is that typically it is that t is greater than n. So panel data would more normally be characterized by maybe you have data on 5,000 individuals and you follow them over 10 years. Or you have data on 100 cities and you're looking at them over 6 different months or something like that. Whereas time series data tends to be defined by t is greater than n. So maybe you're looking at 50 cities, but you're looking at them over 500 months. Or you're looking at 3 stocks and you have data by the minute over 5,000 periods. And so the number of time periods you're looking at is greater than the number of things that you're looking at. And if that's the case, that you kind of have more time series E data, then you have to do the sorts of tests and take the sort of care that I've talked about in this lecture, and that really is kind of just scratching the surface of the sorts of things you might worry about with time series data. All right, so that was my quick overview of time series data. Really, it was meant to sort of just remind you what time series data is and the sorts of things you should be concerned about with time series data, that if your data take a particular form, it might be really easy to get kind of spurious or erratic results, and kind of once again just reminding you that there's a test in economics and econometrics for everything. I'm not expecting you to learn the math of the Durbin-Watson or the Dickey-Fuller test, but you're the sort of econometrician who now, if you know that you need to learn it, I have full confidence that you could go Google the Dickey-Fuller test or look it up in your textbook and be like, okay, yeah, I get it. I get what the intuition of it is. I get what it's trying to do. And so hopefully you appreciate that I'm trying to spend a little less time on the math at the end of the semester rather than making you kind of memorize one more thing. I'm now trusting that you guys know how to fish, that I can tell you that a test exists and kind of what it's for, and that if you need to learn it, you could go learn it for yourself. So that's it from me. I'll talk to you guys in class soon. Hope everyone's having a good last week of the semester. Adios.